Yes, now I'm sharing my screen, right? Is it visible? Okay. So, dear students, let's start it again. Welcome to the day 13 of your digital hardware design course using VHDL for 40 hours. Okay. And today's topic of discussion are counters. Okay. As uh, you know, counters are the very important part of the digital electronics in day-to-day life, and in real life we have lots of several examples, as we have seen when we go onto the road, and we have seen that traffic light controllers are having counters which when down counts for a specified period of time, and then only you can go through to the traffic. Similarly, in doctors, restaurants, we have several examples of counters, right? Accordingly, in digital electronics also, in microprocessor, we need to have in micro. Okay, there where we can uh, okay, there where we can allow the instructions to be executed as per the address available in the program counter. It will count the number of memory locations and allow you to execute the instruction at the specified memory location. Okay, so counters, just like registers, are the digital electronic devices because they are also having flip-flops. They are containing the sequential logic circuits. But we will connect them, these flip-flops, in such a manner that they act like a counter. Counter means 0, 1, 2, 3, 4, 5, 6, 7, right? Or it may be up count or it may be a down count. है ना? Like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Similarly like that. Okay. And frequency division we can use for state sequencing, microprocessor clocks, lots of examples are there where we can utilize all these things. Okay, hope you get my point. Just a second. Right. So today we are focused on some of the types of counters. Okay, types of counters. In digital electronics, you may have come across various types of counters like asynchronous counters, synchronous counters, up-down counters. Okay, and mode N counters, ring counter, Johnson counter. Okay, so these are various types of counter having different types of applications, several applications where you can utilize these counters as per your uh, need. Okay, let us differentiate among all these counters one by one and try to understand how can we design them also. Okay, if we want to design them using VHDL, then how can we design? Okay, if you have any doubt in between, you may raise your hand and Dr. Tukul will unmute, then only unmute you, and then you can raise the question. Okay. So let us first of all understand what is asynchronous counter. Okay. What is a asynchronous counter? So asynchronous counters, sometimes also called as ripple counters. They are also called as ripple counters because they are having a ripple effect. And what is the speciality of these counters? If I say about the asynchronous counters, you can see they are built up of flip-flop only and they are cascaded, put it in the cascaded nature. And in case of asynchronous counters, the clock signal is applied to the first flip-flop and the output of first flip-flop will become the clock signal of second flip-flop. And the inputs of all the flip-flops. will get tied to the logic 1. Oh, this is a T flip-flop you can see over here. And if you remember, the T flip-flop logic or T flip-flop truth table is very much similar to the XOR gate truth table. Means when you have similar inputs, the output is 0, and when you have a different output, then output is 1. Okay, so similar to that, it works. Means if you are having one output, then one input, then output is 0. Okay, when clock toggles, depending upon what was the previous state, what was your previous state. Okay, so basically it toggles on every clock pulse. For the time being, whenever you will apply clock, and if there is a logic 1 tied to T, okay, then whenever clock pulse, the output change on every clock pulse, 0, 1, 0, 1, 0, 1, and so on. Okay, so you may come across this type of flip-flop. You have also learned this type of flip-flop in your digital electronic course, okay, where you have this type of logic. Okay, now you can design this type of counter. Okay, how it works? How it works? When you will apply the clock over here, its output will become 0. Okay, its output will become 0, right? Initially, let's say both these flip-flops are having, let me draw for you. Okay, initially, let's say both these outputs are at 0, 0 position. Okay, now when we will apply this clock, what would happen? Tell me whether my voice is audible or not, please.
Yes, sir, you.
Yes, yes, yes. Okay, so what would happen initially? Let's assume that the output is 0, 0 when you apply the reset. When you will apply the first clock pulse, what would happen? This, due to this logic 1, this flip-flop toggles, and toggles means will change to, the output of this flip-flop will change to 1. Okay, the output of this flip-flop will change to 1, right? And nothing is happen at the output of this. Let me write this like this. First of all, this is QB and this is QA. The output of QA changes to 1 when this clock is applied. It is toggled, changed from 0 to 1, 0 to 1, and this remains same at the first clock cycle. So then you have a 0 1. This happened at first clock cycle. Okay, now when second clock comes at clock 2, what would happen? At clock 2, again this is toggled to from 1 to 0 because this first flip-flop will keep toggling at every clock cycle. It is toggled when again now it is toggled when again because it was previously 0. You can see over here now it is triggered, changing its position, which is acting like a okay. This 1 it is changing from 0. It is acting like a negative as triggered signal for this flip-flop, a valid clock signal. So what would happen? The output of this this flip-flop is also get toggled because it is connected to G. So it is changed to 1. Okay. Similarly, what would happen at clock 3? What would happen at clock 3? Again, this flip-flop got toggled to 1 and there is no change in this output of this clock. It will remain as previous because there is not a valid clock signal occurred. Okay. So hope you understood, and when you will see this count, what is it? Let me insert one more. Uh, insert column right. Okay. So what is this count? If you see 0 0 means nothing, it is 0. 0 1 is 1. 1 0 is 2. 1 is 3. So it is acting like a count. It is acting like a, this combination is acting like a count. Similarly, if you will connect 3 flip-flops, it will become 0 0 0. Similarly, 4 flip-flop, it will become 0 0 0 0. Accordingly, you can increase the number of. Okay. So if you want, you can design this flip-flop. You can design this type of architecture. You can create 3 flip-flops, 4 flip-flops accordingly, and you can create a asynchronous. What you need? We are assuming that initially the count is 0. On reset, the count is 0. Or you can put a clear signal, whatever you want. It may be a clear signal or it may be a reset signal. So I am assuming that we have inserted a reset signal initially in it. Let's say there is a reset signal, right? Either you can make it active low or you can make it active high, depends on this also. As you wish, you can create a signal and then create a clear signal in it, right? It is acting like a clear signal. It is a clean signal. So when it is 1, because it is active high now, when it is 1, the output of this flip-flop is set to 0 0 initially. and when it is 0 and clock triggers, it will count like this. Okay, so you can design this type of counter either using the same approach that we did previously. Either you can use the structural style of modeling, or you can simply design it with the help of a simple behavioral style. In both ways, you can design as you wish. Let me show you. First of all, let me design the simple counter with the help of structural style. Okay, so simple asynchronous designing, asynchronous design of counter. See, as or you can choose you can also choose IP modeling as you wish. Okay, but in this case, what we need to do, we need to first of all design the T flip, right? Because there is a T flip, not a D. Okay, in the previous class, if you remember yesterday, what we did, we have designed the T flips, but in counters generally we use T flip or JK flips. Okay, this you have to remember. Check it out by yourself. Okay, it's like in registers, you see, we are using the D flip flops over here. Okay, but in case of counters, generally we use the T flip flop. So let me copy this uh, code for you people. Okay, we need to design the T flip in the structural style of modeling. Again, I am repeating what you need. First of all, you need to identify the number of modules. Suppose in this example, there are 2 flip-flops. It may be a 3 also, 4 also, as you wish or you want to connect. Okay, so there are, let's say, 2 flip-flops. Both flip-flops are having the similar nature. The clock is negative as triggered. There is a clear signal which is positive as triggered. The T logic is always connected. The inputs are always connected to logic 1. So there are only 2 inputs basically. One is clear clock and another is clear. And there are 2 outputs. One is this and one is this. And these inputs are there, but these are always connected to logic. Okay. So how can we design this? Let's design this T flip-flop. Okay. Just change the name. Entity TFF is, let's say, T clock, and what should I write for here? Instead of reset, let me write clear. Or you can use reset also. And there is a Q out. Okay. And T flip-flop. Architecture T flip-flop underscore arc of T flip-flop is begin T, okay, flop and these. Okay, flop and clear. Okay, right. How it is working? How it is working? If clear is 0, because if clear is 1, then the output will become 0. You can see over here, when clear is 0, the output of this flip-flop is reset instead is irrespective of clock. Okay. Else if, because clock is negative as triggered, clock equal to 0 and clock t given, make it negative as triggered, then what is happening? Output is changing. How output is changing? It is going to not of t. Whatever the value of t is there, the output is changing to not of t. Okay. If t is and T is always tied to, we know, we have tied T is always to, T is tied always to, okay, T is all tied always to, right? T is always over here. What would happen whenever clock comes? The output becomes toggle. If T is 1, the output will become 0 always. Similarly to this, you can see over here, the same logic is there. Output gets toggle. Okay. So, sorry. No, T, we cannot write either. We should write. It should be not of Q. Q gets the value of not of Q. But we cannot use Q over here because Q is an object. So for that, what should I do? Should I have to write here? We check. Should I have tried to create a, let's say I need to create a variable. I will create a variable because variables are input output type. I have told you. So variable u, okay, variable std, because t is tied to, okay, because output gets toggle because t is tied to. Finally, when your process gets completed, okay, so you will, after and it, you can do, you can update the value q, the final. Okay, in this way, you can design this, right? Okay, in this way you can design this. I hope you understand what I'm trying to say to you. Is there any doubt? Please let me know. We have just created a T flip-flop over here, a simple T flip-flop. You can see we have designed a T flip-flop over here because, and in T we know whenever there is a change in input and if input is tied to 1, okay, then what would happen? The output gets toggled. The value of the output gets toggled. If previously it was 1, then it becomes 0. If previously it was 0, then it will become 1. So we need the output and input. We need a variable which is having input output direction, because we need to put it at the input side also, we need to put it at the output side also, at the both sides. Okay, although we are doing it initially 0, but if you want you can initialize it 0 over here also. Okay, that you can also. Finally we are updating this u to the final output. Okay, so when this end of process comes, finally the output will become updated. Okay, we cannot use q because why? because of Q is of output type. We cannot use output variable at the inputs. That's why we have created a variable. In this, how what we have done, you can see what we have done. We have basically created a T flip flop. Okay, and in structural style of modeling, what we need to do? We need to use this as a component so that we can design our main. Okay, so let me copy that main program also so that our time will get saved. This is the main program. We remember these two. This is the main program, right? This is the main program. In structural style of modeling, we need to create the main program. This is the main program. In it, main program is basically asynchronous count. So I will write as like this a count so that you can remember. Okay, we are designing a asynchronous a count entity a count. Similarly, check a count underscore of a count is right. In this, what I need to define? I need to define two inputs. One is TA, another is TB. Plot here and A to B. Okay. I need to call this as a component. If you remember, as it is, I need to call this. Okay. Just replace entity keyword with the keyword component and component. That's it. Nothing we have to do. Right? Apart from that, we need one more signal in it, intermediate signal, if you remember this one. Because its output is going to be connected to the clock of this the clock of this flip. Let's see how can we design it. If we require, we can put a signal, otherwise we'll try to use or port map indirect. So first of all, there are two flip-flops, flip-flop this, flip-flop this. First of all, I will do port mapping for this flip-flop. Okay. So port mapping, doing port mapping for TA. Let me write it TA. I am put T flip-flop A. I am put. Similarly, T flip-flop B. I have to put. Okay. The name of my entity is or file is T. Let me write T flip-flop. First flip-flop is the input TA. Okay. Then I have a clock. Then I have a BTR. And then I have a SQA. Right? Simple. In T flip-flop B, the input is TB. Input is TB. Then in place of clock, the output is QA. In place of clock, the output will be, the input is QA. Right? Because QA will become the clock of second flip flop. So in place of clock, I should write QA, then clear, and then here I should write Q. Okay. So because QA is the output also and QA is the input also. So in place of QA, we may create a signal also over here, intermediate signal also. But let us check whether it works or not, and if required, we can do modification as per our requirement. Okay, and the name of the architecture, that is the name of architecture, that is a count underscore, right? Simple example, we have created a asynchronous design of count using structural style. So I hope there should not be any doubt in it. If you have, you please let me know. Rest, I will test this program for you people on in regard. If you have any doubt, you may raise your hand. You may ask the question. Hope you have previously learned digital these about these counters. आपने पढ़ा होगा पहले, right? So let us test this asynchronous design of counter. Okay, in software as well. Okay, let us write this code over there also and check it out whether it will work or not. Okay. Let me start from here. It will take some time to start. Okay, now create a project. Next, we are going to design a asynchronous counter. So let's write a synchronous count. Next, create a file. We need to create a page. Let's say the name that I should first of all TF. Same name that we have given in that. We have to use the same name over here. Next, we have to choose the book, a usual practice. Then we just ask you to have the entity. We ask you to design the entity. You can change the name of the architecture if you want, or further you have got the option. I will copy paste the code, so there would not be any issue. You can see over here in the software itself that design is created. Okay, this design is created. Let me copy paste this code for our convenience. Okay, see, I have copy paste the code. Same code over here. Library IEEE use this entity T flip flop, T clock clear, and this. Okay, it is giving me some error, syntax error. I just syntax error. Okay, very. I have single quotes. So you can see when you will write code in the software, you will able to get the correct answer, right? Okay, T is the input, right? So we can use it as a a out. Yes, have to apply. In this case, seems like that is acting like a logic. What we do basically, I need to define T as a output, not input. Okay, this is the logic that I need to change, right? I will define T as an output. Always an input, but it is permanently connected to logic 1. So I need to define T as an output rather than input. Okay, T out. Okay, not it. Then it is it plus. You can see now it becomes correct. Similarly, I need to change the following changes. Let me copy paste this. This is the final. Okay. So let us verify first of all whether it is perfectly working or not. Although there is no error. First of all, let us check whether it is working as a T flip flop or not, as we want. Okay. For that, I need to run the simulation, variable simulation. Okay. So you can see it is showing T is always connected to permanently. It is 1. Okay. Because I have automatically specified it always to 1. We cannot force the value on it. Okay. It remains 1 throughout the throughout the simulation process, right? What we need to change? We need to change the clock every time. First of all, we should start with the let's start with the let me force this clock to 0. Okay, and this clear to 1. What would happen when we'll do like this? What would happen automatically? the output changes to reset. Let me run this for a specified period of time. You can see over here, my t is 1, my clock is changes to 0, but irrespective of the clock and irrespective of the input, when clear is 1, the output changes to 0 over here. Now what I do, I will change this clear signal to 0, means I am deactivating this clear signal and I am activating a valid clock signal. Okay. I am activating a valid clock signal. Okay. Initially it is 0 and now I am activating a valid clock signal in it, but my valid clock signal is 1 to 0. Okay, because we have created a negative triggered edge clock. If you remember, we have created a negative edge trigger. So for that, what would happen? Let's see what would happen in that case, because still the clock signal is not a valid clock signal. The output remains same. The output does not change. You can see over here. You can see I have changed the clock signal from 0 to 1, but because this is not a valid clock signal, the valid clock signal would be 1 to 0, because my clock is negative as triggered. Still the output remains same. It is not going to change because I have not got the valid clock signal till now. Let me again change the clock only. Okay, make it 0. Now when I will run, it will be acting as a valid clock signal, and now you can see the change, that it should change from 0 to 1. The output should toggle. Okay, let me run this. Now you can see perfectly it is working. The output gets stopped. Okay, and now every time whenever the clock changes, whenever the clock changes, the output also changes. So let me force this clock now to a clock signal. Okay, let me force this clock now to a clock signal, not I am doing manually, rather than I am forcing a clock, permanent clock. What I will do, I am putting a leading edge value over here as 1, trailing edge value 0, and you can see what would happen. Let me run. Now you can see what would happen. You can see now what would happen. The number of times your clock is triggered from 1 to 0. It is also changing its logic. You can see over here, again it is changing from 1 to 0. This is a valid clock signal, 1 to 0. The output is changes. Now after that, again 1 to 0, the output is changing. So whenever there is a change in the clock 1 to 0, this output changes to, this output get also toggled. Okay, so this is basically a counter. Okay, this is basically a counter type of, you can see. Or in other words, if you see, we have created a clock divider also. If you see over here, what you are doing, are you getting my point? This is a very important concept to understand. Using this, what you have created a clock divider, because in this, during this, you can see 2 clock cycles. For 2 clock cycles, 1 pulse is generated. One clock cycle is completed. From here to here, you can see there are 2 clock cycles. Okay, from here to here, there are 2 clock cycles, and for these 2 clock cycles, we are going to generate 1 clock. If you watch closely, from here. Okay, for this one cycle we are creating this one pulse, right? And again for this another cycle we are creating this another. So for this one clock cycle we are creating one simple pulse. So for two clock cycles over here one clock cycle is connected. So it is simply a divide by two clock generator. You can use this also as a clock. If suppose if its clock frequency is, let's say, 10 megahertz, then if you want to use this as a clock, then it will become a 5 megahertz clock. Okay, so dear students, hope you have understood. Very important, interesting example. Okay, that how can you generate a clock divider in microprocessor architectures. At various places we need to divide the clock also. So it is nothing but it is a clock divider circuit also. A simple T flip-flop acting like a divide by two clock divider. Okay, if you say I will create a screenshot of it for you people, you can remember this screenshot. This will give you some confidence that we have created a T flip-flop, simple T flip-flop. Okay, we have created a simple T flip-flop. Okay, this is the output of T T flip-flop, or a type of divide by or divide by 2 clock divider, right? Divide by 2 clock. Let me paste the this output, simple output. See, keep. Now, but we need to design a counter using that T flip-flop. So what we will do now, we'll any doubt? Is audio not clear properly? Tukur, please let me know. Somebody has messaged me. Dr. Tukur. Dr. Tukur, please let me know if audio is not clear. Now we will create a new file. Okay, over here. The main file for the structural style, right? Create file will do. The name of that file is a underscore count, right? I will copy paste that, no issue. So you can see over here a new file is created. What I need to do, I need to just copy paste the code. This code, but I need to make some changes. Changes should be, first of all, these are no longer be the inputs, other than these are becomes outputs now. Out std which are always tied to. Okay, similarly, we have put it over here. Okay, and my entity should change now. This port logic should change.
here also, right? So I have made the changes over there, so I need to make the corresponding changes over here also, right? Let me copy this code, Control A, Control B, I have done, right? This is my final code for the main program, for the counter, basically a 2-bit counter, you can say a 2-bit asynchronous counter. I am trying to create over here a 2-bit asynchronous counter, right? Okay, now you can see over here, positional port connection error, cannot read from out object QA, use buffer or in out instead QA with mode out. Okay, so what I was telling to you, it is it is giving you the same sort of error. It is providing the same sort of error. So instead of using QA over here, what should we do? Rather than using QA, I would create I have only this output Q, final output, right? Intermediate output I cannot put over here, and I need to define signal. Let's say I will define signal QA over here as std underscore logic. Okay, why I have done this? Because this QA, basically it is the intermediate out. Now if you will see closely or watch closely, this is my entity, this is my entity, okay, and QA is inside this entity, intermediate out. Okay, I am finally getting the output from here, but this is the intermediate out. Okay, right? So let us understand. Because, or I can make this as an input output also, specifically this port as input output also. Okay, but for the timing we are using, there is one more type of direction that is called in out. Okay, I can make it either as in out also. Let me QB as out and QA as in out, then also it works. Okay, but for the timing I cannot use this QA as output over here. Rather than I need to create a signal QA as a signal std underscore logic, because it is an intermediate signal, so it should be created like that. Okay, so this change we have to do in this program. Now let's see over here. After that, let's make it QB. So now everything is okay, there is no error, hope so. And as you will save it, you can see automatically this T flip-flop. You can see this is T flip-flop A, T flip-flop B. These two files will become the component or part of this the main program. Okay, this is the main. So whenever we do this type of work, so this is the main file and it contains two separate files, one for T flip-flop A and another for T flip-flop B. And we have connected them in this manner. This is the port map connections. Now for that, let us first of all check the internal architecture, how it shows to you, and then we'll do the simulation and check the simulation. For that, go to RTL instances and click on schematic. Just see over here. This is the perfect schematic diagram where T logic, TA and TB is there, which are tied to logic 1 in the program. Okay, and this QB, which is a Q output of second flip flop, the output of first flip flop will become the clock of second, right? You can see internal architecture like this. This is the more internal architecture, right? Okay, if you want to go into more deep dive, you can click on these plus buttons also. All right, so this is the simple architecture. Seems perfect. You can create a screenshot of it for your reference, right? We have designed a simple counter. Okay, let me put over here schematic diagram. Okay, for the simulation part, let's see how to verify. How do we have to verify? For the simulation, we need to click on run behavioral simulation. See over here. In the simulation, you find out that automatically, you can see over here, automatically, the T and TV logic are tied to 1 in the main probe. Okay. For running it, we need to, first of all, what we need to do? We need to put clock as 1, let's say, and we need to make clear as also 1, right? And run this for a specified period of time. What would happen? Because when clear is 1, then irrespective of clock and irrespective of your inputs, the outputs will go to 0 state. You can see over here, the output will go to 0 state, right? Now let us change the clock and clear again. Clock force to 0. This time I am taking it as initially as 1 and then 0 because my flip-flops are negative as triggered. So it will act as a valid clock signal in this cycle itself. Okay, so then the output of first flip-flop gets changes. You will see that. Okay, let me make this clear disabled. Right? So when I will run this for a specified period of time, you can see over here automatically the QA output changes to 1. So 0 and 0 1. Okay, 0 and 0 1. Your counter is working. Again, make this clock. Again, make change in this clock. Let's force it for 1. Run this for a specified period of time and again force it for 0. Again, you will find out when I will run this, there is a valid transition of the clock. And you can see both these are changes now. It is also get toggled from 1 to 0, and it is also get toggled because this transition of output QA is 1 to 0, and when it is 1 to 0, it is acting like a valid clock signal for this flip flop TB. That's why its outputs also get toggled, right? So 0 0 0 1, then 1 0. Finally, let me again change the clock. Let me again put 1 and run for a specified period of time, and again run, make it 0. Now when I will run it, you can see both these will become 1. You can see over here. So if I will scroll it from here, you can just watch on these two. Initially it is 0 0, it is 0 1, then 1 0, and then 1. So it is count 0, count 1, count 2, and count 3. So both these inputs together is acting like a simple counter, simple binary count, or a ripple count. If I would be precisely say, it is nothing but it is a ripple count. Right, students? Hope you have understood this concept. Very important concept. We have successfully designed a counter. Let me copy this. You can see this is nothing. This is the example of a counter. Okay, a 2-bit asynchronous count. Similarly, you can make it for 3-bit, 4-bit. If anybody have any doubt in it, please let me know. We have successfully completed the designing of asynchronous counter, ripple counter. You have seen over here. We have successfully completed the designing of asynchronous counter. If you have any doubt, please let me know. I have tried to give you the designing aspects of these counters, how it works. And we have successfully validated also. We have done the verification also. Any doubt, students, please write in chat box. If no doubt, please write okay or something else so that I can understand that you are listening. Please say something, yes, no, understood or not understood. Very good. Okay, fine. Okay. Okay. Thank you. Very, if you understood, that's very fine. So this is all about the asynchronous counters. Okay, this you have learned in your basic digital electronic course, the working, and this the manual designing, right? This is manual designing. But now what we have did we have designed the same thing using VHDL language, and how it does, or how it can be done. That was I told you. We have also learned how to design a clock divider circuit in the form of T flip-flop design. A divide by 2 clock divider. Okay. Similarly, we have finally simulated the final waveform for your asynchronous count. 2-bit asynchronous. Okay, which is showing you that the results are successfully validated. 0, 0, 0, 1, 1, 0, and 1. It is perfectly working as per this truth table. Now let us jump onto the synchronous counters example. What are the synchronous counters? So synchronous counters are also very much similar to asynchronous counter. Why? Because in the terms they are using T flip-flops. You can see over here the JK flip-flops are used, but both inputs are tied. When JK flip-flops, both inputs are tied, they will automatically become T flip-flop. Okay. Maybe you have learned this in your digital electronics. So again, I am taking this example of this. This is an example of the same 2-bit synchronous counter. This is an example of synchronous counter in which you can see what is the difference basically in asynchronous and synchronous counter is in synchronous counters the clock signal is made common to all flip-flops. It is not like that the output of the first flip-flop would be the clock of second. No, it is simply that all flip-flops are synchronized with the clock. Rather, the output of first flip-flop is tied to logic 1, but the input of first flip-flop is tied to logic 1, but the output of second further will work as a input to the output of first will become the input to the second. Similarly, it gets propagated for 3-bit, 4-bit, 5-bit, whatever you want to design. The output would be first flip-flop is tied to the input of the second. Okay, so this is the major difference in between the synchronous and the asynchronous counters. The clock signal basically is synchronous. That's why it is called as synchronous counter. The clock signal is synchronous. Okay, how it works, how it is done, let me show you by the truth table. If you see over here, in this case, assume that there is a clear signal. We are assuming that there is some clear signal. Okay, initially the output is 0, 0. Let's say this is QB, this is QA. So initially the output is 0, 0. So count is 0. Now what would happen when valid clock signal comes? What would happen? Let's see. When valid clock signal comes, valid clock signal means indicative edge triggered clock comes. So this flip-flop and this flip-flop, both these flip-flops get triggered. Both these flip-flops get triggered. Okay, at the same instant of time. Right? And what would be the output of first flip-flop? This one QA. The output of QA would be changes from 0 to 1. And it will become the input to this. Okay? The output of this flip-flop changes from 0 to 1. Okay? You can see over here the output of first flip-flop changes from 0 to 1. Okay, because its input is logic is tied to 1. But now you can see and remember, this changed output will not be input to this clock, rather to this flip-flop. Rather, its previous output, that is 0, is the input to this flip-flop. This is a very important point to note. This is a very important point to note. Please focus on this. For this flip-flop, its previous output is the input, not the changed output is the input. Most of the students made a mistake in this. When valid clock signal comes, its output is 0. Its output is also 0. Previous output is also 0. You can see. So when valid clock signal comes, its output changes from 0 to 1. But because it is 0, its output not get toggled. It remains same. Okay. Hope you got my point. What I'm trying to say to you. Okay. So that's why it is 0, 1. Now in second case, what would happen? Let's see. Now state gets changed. Again a valid clock signal comes, clock 2. When clock 2 comes, this flip-flop again got toggled from 1 to 0. Okay. But the output of this flip-flop previously was 1. Right? So this flip-flop also get toggled. And its output was 0. So it changes to 0 to 1. So like this, 1 0. Okay, I hope you got my point again. Similarly, again when clock third comes, this flip-flop again got toggled because its input is tied to 1. So previously it was 0. Now it is 1. But its previous output was 0, which is acting as an input to this flip-flop. So this remains same as it is. It's not get changed, not get toggled. Okay, so this is what we called as synchronous count. Is there any doubt in the working of the synchronous counter? A simple example to understand. That's why I have taken a 2-bit example so that you will not get confused. Okay, so this is a simple synchronous counter. In this, clock is synchronized to all the flip-flops, and but the output of first will become the input of second. In the previous case, asynchronous case, the output of first will be the clock of the second. But in this case, the output of first will be the input of second clock. Similarly, the output of second will be the input of third, and so like this. Okay. How can we design this? How can we design this? Let's see. We can design this using the similar approach. Same approach, we can design this. Okay. Using the similar approach, we can design this. Synchronous design of counter. In it, you can see there is a JK. We can assume it is as a T. The first flip-flop is tied to logic 1. But the second flip-flop is the getting input from the output of first. Okay. So how can we design this type of counter? So first of all, we need to design a T flip-flop. Okay. First of all, we need to design a T flip-flop. Already we did in previous example. We already designed a T flip-flop. We have a clock, we have a clear. Let us draw clear signal also over here, same. Right? Let us draw a clear signal also in this case so that you can have a clear-cut picture. Okay. let us say this is a clear signal. Let us say this is a clear signal. Just a second. Okay, so hope I am audible. Okay, right. So now we have already designed the T flip flop. You can see over here. We have already designed the T flop. The same T flip flop is there. Similar. Let's say this is T tied to logic 1, clock clear, and this is output Q. So already we have done the designing of this T flip flop over here. Once we have already designed this. Okay, it is there in it. Okay, but here we have made T as a out. Here we have made a T as a out. Okay, so but in this case you can see closely, if you watch closely, that okay, this we can this seems like an input, but because we have to tied it to logic 1 permanently, that's why in the previous case we have made it as an out. Okay, but if you watch closely the second flip flop, this is this with this these two, this is acting like an input to this flip flop, which are getting output or input from the output of the first flip. So it cannot be made output, it should be input. Okay? It should be input, right? So what changes should we make in it to make it correct. That we need to check it out. Okay, that we need to check it out. Let's see. First of all, we have created a T flip-flop in this manner. Now let us see what changes we should have to make in the main program to work is at a synchronous counter as per our requirement. In it, TA, you can see over here, TA is the input. Okay, there is one input. TA is the input, only one input as per the entity. Okay, it should be, sorry, TA is the input. For this it is acting like a output. Okay, for this it is acting like a output because we are tying it to logic 1, so it is acting like a output. Okay, because we are assigning logic 1 to it permanently. Okay, now for this, what we need to do, how do we make it? Let's see. For this, we need to make it as input rather than output. Okay, we need to make it as input rather than output. Or instead of permanently tying to 1 to it, okay, in this particular case, because we need to use it as a component, we need to make it use it as a component. Okay, so we need to tie it as input because for second flip-flop it is acting like a input, right? Because first flip-flop is there, we are replicating the replica of this flip-flop again as a component in the main program, so we cannot define it as an output, it should be input. Okay, so we have to make it as an input over here, right? Okay, so we have made it as input. If we are making this as input, so we cannot use this statement. We cannot tie it permanently as 1 because it is an input. T is input. Okay, input to something, we can pass something on to it through the program. Okay, so during the program, what we will do, we will pass some input to it, right? Similarly, over here, we need to make a TA as input. Similarly, over here, TA as input, your QB as output. Rest of the things are same. QA would be the intermediate. Similar to this, QA is the intermediate part for this. In this case, what I need to do, let's map the first flip-flop. A, first flip-flop is getting input T, TA, clock, clear, then output is QA, right? Output is Q, which is an intermediate signal, no issue, right? Similarly, for B flip-flop, this output will become the input of it because we have taken it intermediate signal, so no issue. This output will become the input of also this. Instead of TB, we should write over here QA because QA is going to be input of this. Clock is now clock, synchronous. Clock is now clock, similar. Same clock pulse is being over here. Clear, and its output is QB. That's it. Right? Simple. Synchronous counter is ready. Okay, the synchronous counter is ready. Okay, a small change we have done only. We have make it as input T, and during the program now During the simulation, we'll pass logic 1 to it and make it permanent logic 1. That's it. Nothing we have to do. Okay. Right. So now design the same code with the help of VHDL and verify it. Okay. Okay. So for that, we should go to File, Project. A new project will create. And this time I am creating this project with the name synchronous count. Synchronous count. Next. Create file. It is going to be a VHDL file. The name of the file is again TF. Okay. I'm using the same code. Next. Check the boot. Yes. It is creating a new project for us. For the timing, make it okay. Just copy this code from here as it is. Right? Just copy this code as it is, just like it is having. Save it. This code we have already tested in the previous program, so it is perfectly working fine. So need not to test it again. We will create a main file again in the same program. Let's name it, let's say synchronous count as count. Okay. Finish. Right. Let's copy this code. Put the name as count everywhere, so that you can remember that this is a synchronous counter. Okay. This will become a synchronous count. Let me copy this. Paste for you. You can see there is no error. Perfect. There is no error in it. It is perfect. Okay. No syntax error. Logical error, I don't know, but there is no syntax error. It is perfect. Logical error will only be checked while simulation after functional verification. But syntax error, there is no syntax. Okay. You can see over here, there is no syntax. Right? Let me save it, and as you save it, again you can see over here automatically these files will become the part of this. You have called the T flip-flop file which we have created over here 2 times for this main project. Okay, when you will see its schematic diagram over here, you can check the schematic diagram. It's the schematic diagram, right? Very similar to that, but in this case you can see the clock signal is synchronous. This T inputs are tied to some TA input, and its output is the input of this. Clear is common, clock is common, QB is this there. Okay, if you want, you can take the snapshot of this for your reference purpose. Just I did for every case. Make a copy. The functional verification and simulation of functional verification and simulation department, policy. Right now, after that, let us run this and check it out whether it is working or not. Take the simulation, do the simulation. Okay. Now here you can see the TA is not connected to any logic permanently, rather it is now input. And it is our responsibility now to force it to some value. So force on it 1 permanently. Okay. Let's make clock 0, clock 1. Sorry, because negative as taking we need to create. So we'll make initially it is at 1. Let's make clear as 1 because initially we want outputs to be clear. Okay, we want outputs to be clear. Right. Let us run for a specified period of time. You can see the outputs are 0, 0. Okay. Now make clear 0 permanently, and this TA should not get changed throughout the program. This clock we need to change constant from. Okay. Now run for a specified period. Now you can see in it both the outputs gets changed. So there is some the outputs in it. The first flip-flop gets also toggled and second flip-flop also get toggled. Sorry, both the flip-flops get toggled at the same instance of time, but it should not happen because why? Because the output of first is the input of second. And if the output of first is the input of second, then it is also changing from, it is changing from 0 to 1, but it should not get changed from 0 to 1. It should be remains at 0. But previously the output of QA is 0. It should add, it should not get toggled. It should not get toggled. There is some there is some mistake. Why it is happening? Let us verify the code itself. What it is doing. Actually, if we will focus on it, TA is getting 1, it is get triggered, it is creating a QA output. Okay. The clock signal. Previous output of Q is 0, it will toggle it, not you, at every clock edge. Let's change this variable. See, because what is happening actually, this output we are getting, it is this flip-flop will getting the updated output. Whatever the QA gets the new value, it is taking that new value. But what we want it to take the previous value of QA. So we have learned the concept that in variables, whenever we make a variable, its output is updated instantly. In variable, the value is updated instantly. So Let me try and check it out. What if it will make it signal rather than variable? Is there any difference in happened in the program? Let me check it and then see whether there will be any change in the program or okay. Let us see if a small difference would work or not. Okay, let me update this program again in the T flip-flop file. Okay, save it, close the simulation. First up, okay, let us close the simulation. First up, make the necessary changes where as required. Okay, we have make the changes, right? Rest of the things are same. No error. There is no error. Okay, now run the simulation and check it out. Let me cancel it once. It's saying elaborate design is out of date. Design source were modified. Reload, yes, reload. Okay, changes are now applied. Whatever the changes we have created in this program, these are applied at respective files. These files are now updated. The changes. Let me close it. Now run the simulation. Um, let's check whether this small change is working or not. Okay, right? Or otherwise, we will try to find out some other solution later on. Okay, if it is not going. So let us try to force constant, make it 1 permanently. Then clock we need to change, make it 1 initially. Clear we have to make. Okay. Now let us run for a specified period. Okay. In that case, the output is not get it's not getting the update. It means it is not working. We are getting the updated outputs. Again, we need to check the design. So you can see, in spite of that, there is no syntax error, but still we are not getting our required output. We need to keep updating until and unless we are satisfied with this. Okay, We have to check where we are basically finding difficulty. Okay, we have created as a variable. I'm saying if this is 0, please update it. Okay, and this is event, then do this. So actually, I need to put this inside the statement after this statement. Okay, again, reload this design. I'm going to this change last. If it would not work further, then see the things later on. Okay, let me run this simulation. Let us again try to do it. Force constant, clear, make it clear. Force value, right. Again, it is giving the error. It means the logic that I am trying to change, it is not working as per my requirement. So what I will do, I will try to do it by myself, and then tomorrow I will come up with the solution. Okay, where we are getting logical error. This is a logical error. Syntactically we are correct, but there is some logical error which we are doing. That's why outputs are not updating. Okay, so this is again, till now you have seen I am writing the program and it is perfectly running. But this is also a learning. You can see over here, if I am not getting the correct output as per my, I am not functionally verified it, the design that I have created is of no use. The code that I have written is of no use because it is not functionally correct. So that's why we do the functional verification after each design, making each design. And when we are satisfied with every test case we have to check. We cannot miss a single test case. So for when we are satisfied with the every test case, then only we can further do other things. You can see over here synthesis, implementation, and other processes which we have not discussed till now. But in future lectures, I will let you know about the importance of these steps also. Okay, so before jumping onto this, we need to perfectly check it out whether our simulation or our functional verification is perfect or not. Because if you go further directly by missing any step, then at the final stage you will find out that you have wasted lots of money and you are getting a wrong IC to be get manufactured. Okay, so for the day I am closing. If you have any doubt, you can write in the chat box. Okay, I will try to answer. But for the day, I am closing the session. Okay, please let me. And if you have any not having doubt, you may leave for the day.